The objective of this video is to read through the lecture notes of the course EE275 Electromotor and Motion Control. We will begin with Chapter 1, Modeling of Electric Machine. The model of electric machine really has two parts, one including electrical dynamics and mechanical dynamics. We will first review the Newton's second law of motion. So the Newton's second law of motion is really involving one concept known as momentum, denoted by p vector. It is equal to the mass of a point particle times its velocity v. Newton's law says that the time derivative of this momentum is equal to its force. And if the mass of the point particle is constant, and this formula really tells us a way to measure the mass if we know the speed and the force exerted on this point particle. To do that, for example, we can make sure the particle is in some circular motion, and we learned that from our high school courses that the centripetal force F is proportional to the mass, the velocity squared over r. But how does this result come from in the first place? So if we look at the Newton's law and we rewrite it into its component-wise form, we have fx, fy equal to the derivative of vx and vy. And we can apply some constraint that we know it's our point particle is in circular motion at a constant speed. That's why we have the amplitude of the velocity is constant, and we know that the force and the velocity is really orthogonal to each other, so their dot product is really 0. But I stop here because I don't know how to proceed. Instead, we often take a different approach to change the reference frame. So, but before we do that, we need to again review how to take time derivative of a vector. A vector r can be rewritten into its into different form in terms of its component rx, ry, and rz, and unit vector x hat, y hat, and z hat of this Cartesian coordinate. By taking time derivative, we really need to take time derivative of both component and the unit vector. But we know that the time derivative of our unit vector is 0. That's why we reach this natural result here. But now consider there is a different reference frame denoted by dqn that's spinning at an angular speed vector r in space. We can express our vector position vector r in terms of its components in dqn frame, and the unit vectors d hat, q hat, and n hat. Now, if we take time derivative to this vector, the expression becomes a little bit messy because the derivative, for example, of unit vector n hat is never 0 anymore. So apparently we can rewrite n hat, the time derivative of n hat into in terms of omega. To see that, let's assume there's the omega hat vector is like this, have n hat vector here, and we assume the angle between n hat and omega is theta, and n hat is spinning around the axis of rotation that's denoted by the direction of the vector omega. So we can draw this cross section view here. So basically our n hat is first evaluated at this point A, then after some time dt, the end of our vector n hat moves from point A to point B. The angle moved is really omega times the time elapsed dt. The radius of this circular motion is really simply as sin theta. To see that, we know the unit vector n hat has a length of 1, so that's why the radius is really simple. It's sin theta. So omega dt times the radius sin theta is the arc length. So it's this part, this length. This length over its time is really the speed of n vector n hat. So we can rewrite this expression further. Is rewrite it into omega times 1 times sin theta. So 1 is really the length of n hat. So this is basically the cross product between vector omega cross product n hat. So that's why we can rewrite this time derivative in terms of omega and cross product. So basically, by doing this, we can avoid taking time derivative to unit vectors. To express this explicitly, we use subscript dqn to remind you that we don't really need to take time derivative of the unit vector dqn anymore. So basically, we are going to arrive at this result that taking time derivative in xyz frame is equal to time derivative in the dqn frame plus some rotation-related term. We are interested in this result because later in this electrical machine modeling process, we often do change of reference. For example, we can replace this position vector r with some other physics variables such as flux linkage. So it's denoted by this psi symbol here. The term here, we need to make sure the omega sin, the synchronous angular speed is really a vector here. This voltage term here does not really exist in reality, but it is famous and it goes by the name of rotational back EMF in the motor control textbook. Later, we will also see that there is like analogy between Newton's law of motion. So force equals to time derivative of the momentum between the law of induction by Faraday, that the EMF applied to a coil is equal to the time derivative of the flux linkage. So basically, the momentum for a coil is also known as flux linkage. The force applied to a coil is basically the back EMF. So since we have this fictitious voltage here in our circuit, we can imagine there's also fictitious or there's like pseudo force known as inertial force in classical mechanics. To see that, we need to take another time derivative to both sides of this equation, because omega times position vector is really only speed. We need to take another time derivative to get force. We can reach this equation 9 here. Here, basically we take another time derivative in the dqn frame. And remember, we want to avoid taking time derivative of the unit vectors. That's why we use this plus omega cross term here. Finally, after some tedious derivation, we finally reach at this result here. So if we replace this term with force vector F, we can actually drop all these subscripts that denote our time derivatives only valid to the vector components. So we can basically rewrite our Newton's second law of motion in some non-inertial frame of reference denoted by dqn. So there are three pseudo force, or you can say inertial force, that's known as Coriolis force. So it has name here, Coriolis force, centrifugal force, and Euler force. And in particular, we are interested in a constant angular speed circular motion of a point particle such that its velocity in dqn frame is 0. That's why we have a Coriolis force is 0. and the speed of the frame is constant, so the Euler force is also 0. And note our point particle is at still in this DQM frame. That's why its acceleration is also 0. That's why we finally derive the result of centripetal force. So the centripetal force is equal to the negative of centrifugal force, and if we make sure that omega vector is orthogonal to our position vector, then we finally derive this centripetal force result that we have learned in our high school. It is really safe to skip this subsection for now because we don't really study circular motion of a free particle later. But this section is worth a reread after you have learned the Park transformation that we use later for modeling of electrical machine.